Hello everyone, this is the third lecture of Audit Analytics course. This week, we have Professor Qi Liu to present the descriptive statistics. Before we started, let me give you a very quick review of what we have covered in first lectures. In the first lecture, introduction part, we have discussed what is data analytics and how it can be used in contemporary business environment. Dr. Vasarali shared some cases about the usage of data analytics in business area. From these cases, we can see that by using different data analytics methods, machines can make better predictions than human beings in certain scenarios. This is due to cognitive limitation of human brains. We also covered a little bit about big data, which is a heated topic in current business environment. We will continue our discussion on big data on 12th week. The existence of big data is also the motivation to have data analytics. Finally, we discussed the concept and the usage of audit analytics and how we can combine audit analytics with forensic analysis, forensic experience, and real-time technology. In the second lecture, we introduced several audit analytics-related software tools that can facilitate auditors to perform audit analytics tasks. First, we introduced two products that are designed for audit purposes, Caseware Idea and ACL. We will start to use them on 5th week. We also covered and downloaded other general statistical packages, including R and Weka. Qi Liu will be using R in this lecture, and she will be using both R and Tableau Public for next lecture, data visualization. So I hope you have already installed R and R Studio on your computer.
In today's lecture, we're going to talk about the first step of the audit analytics, which is the descriptive statistics. After getting a data set, the first thing that auditors have to do is try to understand the data. And one way for the auditors to get a general understanding or overview of the data set is the descriptive statistics. We can see that the descriptive statistics are routinely used in reports which contain a significant amount of qualitative and quantitative data. And it can help summarize and support assertions of facts. And one important thing is that unless descriptive statistics are fully grasped, data can be easily misunderstood and misrepresented. Also, a thorough understanding of descriptive statistics is essential for the appropriate and effective use of all the other advanced tests, like the analytics that were covered in the following weeks. So the descriptive statistics are usually used in the preliminary analytic procedures in the audit planning process. The auditors can use descriptive statistics to get a general understanding of the client's business. And descriptive statistics can be used as the first indicator for the anomalies. For example, if we find some data unreasonably distributed according to the descriptive statistics, then we may want to focus on these areas and do more tests. Since descriptive statistics differs according to different data types, first I'm going to give you some background information about the data type, and their features. Generally speaking, there are two types of data, the qualitative data and the quantitative data. The qualitative data, we can also call it categorical data, which have exact values that can fall into numbers of separate categories with no possible intermediate levels, which means that there are no intermediate values between each category. And there are two types of qualitative data, the nominal and ordinal. And the quantitative data, we can also call it continuous data, that the difference between values is both meaningful and allows statements about extent or degree. Like usually the example of quantitative data, like the payment, salary, or the age, etc., etc. And now we're going to look into each type of this data. This slide shows the features of nominal data. Like it's an unordered qualitative data, the categories of a nominal variable have no relation to each other and cannot be arranged in a specific order. If there are only one of two alternatives, the nominal data is dichotomous, like gender. And if there are more than two categories, the nominal variable is multichotomous, like blood group, occupation, etc. and etc. And the second type of qualitative data is ordinal variable. It's an ordered qualitative data. The values of an ordinal variable have natural order or progression. For example, if scores are assigned to rank individuals, like a student's level grade, the ordinal variable is score ranking. And if the ranking occurs for a group of responses, the ordinal variable is categorical, like social classes. The most confusing type of ordinal variable is the numeric discrete, where a number is assigned but doesn't mean a true quantity, like the size of clothing and the shoe. We have the numbers for the different size, but this numbers doesn't mean a true quantity of the shoe or clothes. Then let's take a look at the continuous data, which is also called the quantitative data. For the quantitative data, we can see from this figure that we usually have intermediate values between each values, and we can have negative values for the quantitative data. And the most important thing that we can do the mathematical operations on the continuous data. Well, then we compare the continuous data to the numerical discrete data, which is one kind of ordinal data. We can see that for the numerical discrete data, there are no intermediate values between each value, and the numeric discrete data don't have negative sign, and most mathematical operations cannot be performed. And if we use the mathematical operations on this nominal data or numeric discrete data, usually will produce meaningless results. Okay, now we have got a basic understanding of these two data types, and then we are going to introduce the descriptive statistics for each type of data. First, let's focus on the qualitative data. For the qualitative data, we can do the following descriptive statistics, like the frequency distribution, the relative frequency distribution, and the category statistics. I'm going to demonstrate these descriptive statistics using a dataset called the employee master data. There are 42 records in this data, and this lists all the attributes in the dataset. The auditors will use this data to do the analysis of the payroll information. Okay, so in today's demonstration, we are going to use one attribute as example, which is the work department. I'm going to show you the descriptive statistics on this attribute. Okay. So the first descriptive statistics I'm going to show you is the frequency distribution. The frequency distribution of a data is a summary of the data occurrence in a collection of non-overlapping categories. And for the employee master data, because each record in the dataset represents employees' information, so the frequency distribution of the work department is a summary of the number of employees in each department. And this table shows the result of these descriptive statistics. We can see that for the work department A00, there are 5 employees. And for this work department B01, there are 1 employee. And for work department C01, there are 4 employees, etc., etc. Okay, now I'm going to show you how to do this frequency distribution analysis using R. Because in this course, I also want to show you how to use this software. So I'm going to demonstrate a whole process of doing this analysis, which starts from the import of the data. Okay, so let's take a look at the data first. I store the data in the C disk. So let's go to my computer and the disk C. Here is the data. The employee master data is delimited file. Let's open it using Notepad. Then you can see that here is data. You can see the first row of the data is the name for each column. And then we have several columns which include the employee number, the first name, the last name, address, etc., etc. And the data is separated by tab. Okay, then let's go to R. Go to our program, start our program R, and then open it. Here is the interface that we have discussed in the last lecture. Then we will click File, open New Script. There is an interactive window. Then we click Windows. You can choose how to display these 2 windows. Like I try to display it vertically. Then we could type the R command here and see the result here. Okay, first let's start the import process. In R, for convenience purpose, we usually need to assign a name for the data we are going to import it. Like here, I'm going to use the imp master. You can use either lowercase or uppercase, but R is case sensitive, so if you use lowercase in the first time, then for the rest of your analysis, you need to use lowercase throughout all your analysis. Okay, then a function we use here to import the table is called read table. Then we type the parentheses Then we need to enter a pair of quotation mark. Inside the quotation mark should be the location of the file that you want to import. Like we just stored the data set in C disk, so I type C is in master dot df. Okay, since this data is separated by tab, we should also tell R how to read the data set. Could define this, the separator equals to, this means tab, and then as you also seen that there is the first row of the data is the name of each column, so we don't want R to read it as the value. So we need to tell R that the header is true, so we have header in our data. Then we just right-click it, run the scripts. Okay, you can see that the script is in the right side. And then we can enter the name of this table to see whether R has imported successfully. Employee master. Then we run this again to see, we can see the data in the right side. You can see that it has employee number, has first name, last name, and address. The data has imported successfully. Okay. I have all these attributes. Because in our analysis, we only want to use one column in this data. This is the work department here. So we have to choose this column from the whole table. Okay, change another line. We entered work with assigned a name for this column, work department, we just call it, and it's equals to the master. This infers this table. Okay, then we use a dollar sign to indicate the columns. Then we need to type the column name. It's the work. Remember, it's case sensitive. The first letter of the word work is in uppercase, but the others are in the lowercase. So we should just copy it exactly. And then the underscore, capital D, then the lowercase EPT, and underscore. Okay, so this refers to the column work department in the table employee master. Then we need to use the dollar signs to connect them. Okay. Then now here, let's see, have we choose this column successfully? Then we just type the name of the column. Okay, then we select all the scripts that we want to run, then choose run. Then you can see that. Okay, now we can see that the work department here means a set of values that is same as the values in the column. Here we can see work department column in the employee master dataset. It also shows the unique values in the work department column. Okay, then we start to work with the values in this column. Okay, then next we just need to calculate the frequency of this column. Then we use a function called work department dot frec, indicate the frequency of this column. Then we use a function called a table. And we just type the work department here. This means all the value here. Then it will return the frequency distribution of this value directly. And the work department frequency. Let's just see the results. Then we choose the scripts we want to run. Then run the line of selection. You can see that here shows the frequency distribution of this column. You can see there are 5 employees in the department A00, 1 in the B01, 4 in the C01. Let's compare the result to the results we have. It's the same. Okay. So using this function, you can get the frequency distribution very quickly. Okay. So this is the first task we have done with R. So you may say that I know nothing about the R command. Then how can I know which function to use? So in this course, I'm going to teach you several functions that are related to different statistics. And also for each function, there are several parameters. Like here, the read table, you have the separator, the header. Then you may not know all these parameters, but in R, it's very convenient that if you know the function, like here, you want to know the detailed attributes that you can add or you need to specify for this function. You can usually use another function called help. So you just type help and then enter the name of the function, like read.table. Then you run this. It will bring you to a web page that tells you how to use this function. It shows you the description of this function and the format for the function and its variations. And also it lists all the parameters that you can add or specify in this function, like the header, the separator, or you can add the row names, the column names manually, or a lot of different parameters. So it's very convenient. And also, for the functions, if you want to know more about the R, that you want to use the functions that we didn't cover in the class, you can always Google it. For example, for this frequency distribution, you just need to Google frequency distribution, then R. Then you can see the functions you will be able to use to achieve your objective. Okay, then let's go to the next descriptive statistics for the qualitative data. It's the relative frequency distribution. The relative frequency distribution of a data is a summary of the frequency proportion in a collection of non-overlapping categories. And the formula to calculate the relative frequency distribution is here in the slides. You can see that we just need to use the frequency to divide the sample size, like the total number of records in the data set. Okay, let's take a look at an example. Here, we still use the employee master data and use a column of work department. And so we know that the frequency of the different values in work departments is here listed here. Then we just use the frequency divided by the total number of records in the data set, which is 42. Then we will end up with the relative frequency. And we can see that the total of relative frequency will equals to 1. Okay, then let's take a look at how can we do this in R. Okay, let's go back to R here. Then now we have already have the frequency distribution of work department. We have already assigned a value for this. And now we need to assign another name as the relative frequency distribution. We call it work department relative frequency. And we use that formula to calculate the value of the relative frequency distribution. It's just the work department frequency divided by the number of rows. Here we use another function called nrow, which will calculate the number of rows in the table employee master. Okay, then let's see the result. Okay, let's just select this scripts and run it. You can see that here the result, we just divided the value of frequency distribution to the number of rows in the employee master data and got the result, which is equals to what I showed you before. Even though we don't have a specific function that's designed to calculate the relative frequency, we can also define a formula by ourselves for R to calculate this relative frequency. It's pretty easy. Okay, then the next, this descriptive statistics for the qualitative data is the category statistics. Usually the qualitative data can be classified into categories according to certain attribute. Like here, the employee master data can be categorized in different work departments. So for each category, we could use some different statistics to describe the characteristics of these categories. For example, we could summarize the salaries for all the employees according to the work department. Then we can see that for each work department, what is the average salary of the employees. Okay, here this is just an example of the average salary for each work department. Okay, then let's see how to do this in R. Go back to R. Here we use another function to do this task called tapply. This function you will use to do the calculation by groups. Then let's see. We just need to first enter the column that we want to do the calculation on, which is the salary. Okay. Employee master $sign salary. Then we enter the column that we want to use as a group indicator. Then here is the work department. Work department. And now the calculation. And now we should specify the calculation we want to do. Here we just want to calculate the average salary for each work department, so it's just the mean. Okay. Then we just need to run this. Okay, here it shows the results. For the, we can see that for the work department A00, the average salary is 40,855, and then etc. for the others. You can see that. Also, it's not just to calculate average. We can also calculate the total salary for each department, or the maximum salary, minimum salary for each department. Now let me show you how to calculate the total salary for each work department. So it's very similar. So we could just copy the old script and paste it, but just change the mean to the sum, which means the total. And then just run this. You can see that here are the total salary for each work department. Also, you can do the other kind of calculation just as you want. And I will also show you a lot of different descriptive statistics for the quantitative variables like the salary, just in a few seconds. Okay, so now we have covered all the descriptive statistics for the qualitative data. Let me do a little bit review of this. So basically there are three kinds of descriptive statistics for the qualitative data. It's the frequency distribution, the relative frequency distribution, and the category statistics. Okay, now let's move on to the descriptive statistics for quantitative variable. Here we have more descriptive statistics for qualitative variable. Now it includes the frequency distribution of data, just what we have discussed for the qualitative data. But there are several other kinds of frequency, include the cumulative absolute frequency and cumulative relative frequency, which we are going to discuss later. And also there are type of descriptive statistic is called the central tendency of data, which is showed where the data tends to fall, and is usually measured by the mean, the median, and the mode. And another kind of descriptive statistics is the dispersion of data, which shows how spread the data are. And usually it is measured by the variance and the standard deviation, like that. And another two kinds of descriptive statistics for quantitative data is skew of data, which shows symmetry of data. Like you can see how concentrated data are at the low or high end of the scale, and usually measured by the skew index. And another kind of descriptive statistics for quantitative data is the kurtosis of data, which indicated the peakedness of data to show how concentrated the data are around a single value, which is usually measured by the kurtosis index. Okay. Then let's go first to the frequency distribution. So like we can see that in the qualitative data, usually we have the categories for each data, so we can calculate the frequency distribution according to these categories. While for the quantitative data, we don't have the naturally formed categories. So we usually group the data into several classes, and to calculate the number of data points that fall into each class. Frequency distribution is always the foundation of descriptive statistics. There are four kinds of frequency distribution that we're going to look at for the continuous data. It's absolute frequency, we already talked about, the relative frequency that we also talked about for the qualitative data, and then the cumulative absolute frequency and the cumulative relative frequency. This not for the qualitative data, just for the quantitative data. The data I'm going to use to demonstrate the descriptive statistics for the quantitative data is the payroll data, which have 44 records and have several attributes. Here, like the employee number, the work department, the gross pay, taxable amount, net pay, pay dates, and check number. And the attribute we're going to use here is the net pay. The reason why I choose a different data set to demonstrate the quantitative data is that I'm trying to show you again the data input process for you to get more familiar with the software. Okay. The first type of frequency distribution for the quantitative data is absolute frequency. Now here you can see that in the row data, let's go back again. Here this column shows the net pay of the employees. We can see that the range for this column is around from 1,000 to 4,000. Then we try to group the values in the net pay attribute into 6 groups. The range for each group is 500, so that we can see that here is the groups. The first group is from 1,000 to $1,499.99, and then the second group is from 1,500 to $1,999.99, and etc., etc. And here we calculate the numbers of records that falls into each of these groups. It's just like the frequency distribution for the qualitative data. Okay, so I don't want to explain more for this because we already talked about this in the qualitative data. And then the next thing is a relative frequency for the quantitative data. It's also the same thing as the relative frequency for the qualitative data. It's just for each group of the quantitative data. And we can also see that the sum of all the relative frequency equals to 1. Then another frequency that we haven't covered in the qualitative data is the cumulative absolute frequency. This table includes the cumulative absolute frequency. Compare it to the absolute frequency, you can see that for absolute frequency just calculates the number of records for each category, for each class, while the cumulative absolute frequency doesn't show the absolute number of the records for each class. Instead, it calculates the number of records that falls in one group and then add the number of records that falls in its previous groups. For example, for the first group, it don't have any previous groups, so it just calculates the number of records that falls in this group. While in this group, we calculate the number of records in the second group is 23, and then we add the number of records in its previous group, which is the first group. This is 13. So we add them up and then get the 36. And then for the third group, then we calculated the number of records that falls in this group, which is 2. And then we add the number of records that falls in its previous groups, which is a total of these 3 groups. Then we get to 38. And for the rest of groups, is the same. So for the last group, we end up with the total number of records that in the whole data set. The reason why we include this cumulative absolute frequency to describe the quantitative data is that it shows a summary of data frequency below a certain level. For example, we can see that below like 3,000, there are 41 records. But we don't include this to describe the qualitative data, is that we cannot compare the categories in qualitative data. So it will be meaningless to calculate this cumulative absolute frequency. Okay, then the next frequency distribution is called the cumulative relative frequency. It's just like the cumulative absolute frequency, but also divided by the total number of the records in the whole database. And we can see that for the last category, the cumulative relative frequency will equals to 1. Okay, then let's take a look at how to get these statistics in R. Then we go back to R, and you can see that first let's go to data. The payroll data is here. Store it in the C disk. So let's just do a little review of how to import the data. First, we assign a name for the data. Payroll is equals to read table. C, it's in the C disk. Payroll.txt. Because this is just a text file, so we don't need to specify the separator of this file. And let's take a look of the file. Click into it, so you can see that there are also headers used as the first row. Okay, so we still need to choose header equals to true. Okay, then let's see the data in R. Just choose these 2 lines of scripts and run them. You can see that R reads data successfully. Okay. Then again, we choose the field that we're going to use, the net pay. Name it as net pay, which will be equals to the payroll dollar amount, the net underscore pay. Okay, then let's take a look at the variable. Okay, we got all the values here. Okay, then it doesn't return the unique values because it is continuous value. Now we are going to try to group all these values of net pay into these classes. And first we have to set rules to this classification. Okay, then we use give the name of these rules of break. We name this rule as breaks, and we define this by first generate a sequential number. I type seq. This function will generate a sequential number. Then first we input the start point of the number, which is 1000.0, because all the values here in the net pay have 2 digits after the decimal point. Then we need to enter the upper bound of this sequential number, which is 4000. And we want to divide these numbers by 500. So the range of each class will be 500. Okay. Then we need to assign these points according to this row. Okay. We name this as netpay.cut because we're going to use the function for the cut to do this assignment. Okay. First, we need to type the numbers we want to assign. It's just the net pay and the rules, the breaks, and you can see in our slides we show that we want to put the 1500 this value into the second group. So we want to leave it the upper bound of the first group open, so it should not be closed. Otherwise, this 1500 value will be located into this group, the first group. Okay, so here we use a parameter called right, which means whether the right side bound of each class will be closed or opened. We just want to leave it open So we type it false. You can check all these parameters by using help function. Okay. Okay, let's see what happened now. Just select this and run. Okay, we can see that each of the value here in the net pay are assigned to these groups, and there are 6 groups here. You can see 6 different groups here. Okay, now we can treat it as qualitative data to calculate the frequencies. First is absolute frequency. We call this the net pay dot frac, which equals to table net pay dot cut. Okay. Then we may want to see this like frequencies in the table view. So we use another function here to display the results in tables. This is called cbind, which could show the results by columns. Okay, so we just use it to show the net pay dot frac. Okay, then let's see the result. Here shows the result. Like for the first category, there were 13 records, and for the second one, there were 23. And there are 2 for the third one, 3, 2, 1 for each of the following classes. Okay, then the next thing we want to show is relative frequency table. As we do this for the qualitative data, we do this again here. First name it at net pay relative frequency, which equals to net pay dot frequency, but divide the number of rows in the payroll table. Okay, then we also want to show this in the table view, so we just still use cbind function. Show the net pay frequency and net pay relative frequency. We want to see all these frequencies in the same table. Okay, then let's see the results again. Here, it shows the results. Okay. It's just like what we did for the qualitative data. And then for the cumulative absolute frequency distribution, still it's very similar. First assign the name for this calculation, cumulative frequency. Okay, there is a function called qsum, which is used to calculate the cumulative sum for a set of numbers. We use this to calculate the net pay frequency, and then we just need to see this in the same table. See this 3, frequency distribution in the same table. Qfreq. Okay. So we run this. Here is the result. Exactly the same as I showed you before. Okay. Then for the relative frequency, we define it as relative cumulative frequency. We still don't have a function to calculate the relative cumulative frequency distribution, but we use the results of the cumulative frequency to calculate it. It's the net pay cumulative frequency divide the number of rows in the payroll table. Very similar. Then we want to see all this frequencies in the same table. Net pay relative frequency, the net pay cumulative frequency, the net pay relative cumulative frequency. Okay, here we will be able to have a complete view of all these frequencies. Okay, so these are for the frequency distribution of quantitative data. Okay, the second type of descriptive statistics for the quantitative data is called central tendency. This descriptive statistics is used to indicate the middle and commonly occurring points in the dataset. There are three main measures for the central tendency. These are mean, median, and mode. Mean is sum of all the values divided by the number of the values in the dataset, which we can also call it as average. The mean may not always be the best measure of central tendency, especially if data are skewed. For example, the average income is often misleading, since those few individuals with extremely high incomes may rise to overall average. And that's why we need to add some other measurements for the central tendency. And the second measurement is median. Median is a number that at most half of the value are below it, and at most half of the value are above it. It is usually used in statistics because this value represents the exact middle of data that's better than mean, so that 50% of values would above or below the median. The third measurement for central tendency is mode, which means the most frequent value in the data. The mode is the least commonly used measure of central tendency, particularly in large data sets. However, the mode is still important for describing a data set, especially when more than one value occurs frequently. In this instance, the data will be described as bimodal or multimodal, depending on whether two or more values occur frequently in the dataset. Okay, now let me explain these measurements one by one for you. This table shows the sample data, and the last row of the table shows the sum of the of all the values in this data set. Okay, and if you count, we can see that there are 10 records in data set. So the mean of this data is equals to 40 divided 10 equals to 4. So by calculating the mean, we use every single value in the data set. Okay, then let's go to see the median. This is the same data, but if we want to calculate the median, we have to sort the data first. So here the second row of this table shows the sorted value of the data. And since we have 10 records in the data set, which is an even number, so we have to add the fifth and the sixth value together and divide it by 2 in order to calculate the median. If we have, for example, 9 records or the other odd number of records in the data set, we just need to pick the value that's in the middle of the sorted values. So we can see from this example that unlike the calculation of the mean, which we use every single values in the data set, we only use 2 central values to calculate the median. So the median is not sensible to the extreme values. Then let's take a look at an example of the mode. So we use the same data set in this example. Let me just refresh you a little bit that the mode means the number that exists most frequently in the data set. You can see that in the data set, we have 5 exist in the data set for twice, and 7 also exist for twice. So we have 2 modes, 5 and 7. Okay, then let's take a look at another example where this is another data sample where we have 1 exists in twice and 3 exists in 3 times. So the mode of this data set is 3, and there is only 1 mode in this data set. What if every single value in the data set is different? Then this data set doesn't have any mode, and it is also possible. Now let me show you how to use R to calculate these measurements. Okay, let's go to R first. Here we still want to use the values in net pay column as the sample data. Okay, so first we just need to calculate the mean of these values. So there is a function called mean in R. So it's very easy. Just type mean and to calculate the mean of net pay. When we run this, here shows the result. The mean of net pay is 1,810 and 646. Okay, so next, let's calculate the median. The same, there is a function called median in R. So we just need to type median for the net pay. Run the script. Here shows the median of the net pay is 1,743.34. Okay. Then for the mode, there is not built-in or existing function in R for us to calculate the mode. But one way we can tell or we can see the mode is to use the frequency. For example, let me show you the frequency of the net pay. Just there, use the same function that we used for the qualitative data. It's here, like here, we use the table, okay? So the function is table, and we use it on the value of net pay. So it returns the frequency of each values that exist in the net pay column. So you can see that there are several values that exist twice, and there are one value that exists 3 times. This is 9743.34, and this is the mode. So we can easily tell the mode of a continuous data using the frequency. Okay, so that's for the central tendency measurements. The next type of descriptive statistics for the quantitative data is dispersion, which is used to indicate how spread out the data are around the mean. And the most common measures for the dispersion include the range, variance, standard deviation, coefficients of variation. The range means the distance between the lowest and highest values in the dataset. It generally describes how spread out the data are. And the variance is the sum of the squares of the differences between each observation and the mean, which quantity is then divided by the sample size. Variance is used less frequently than the standard deviation as a measure of dispersion. The variance can be used when we want to quickly compare the variability of 2 or more sets of interval data. In general, the higher the variance, the more spread out the data. And the third measurement for dispersion is standard deviation, which is the positive square root of the variance. It is average differences between observed values and the mean. The standard deviation is used when expressing dispersion in the same units as the original measurements. It is used more commonly than the variance in expressing the degree to which data are spread out. Another common measurement for dispersion is coefficient of variation, which is the relative dispersion by dividing the standard deviation by the mean and then multiply by 100 to render a percent. This number can be used to describe the variance of 2 datasets better than standard deviation. Okay, then let me use some examples to show you the meanings of these measurements. First, the range. Now here is the first example. This shows a set of values, and the range is the largest value minus the smallest value, which is 6 minus 1, which equals to 5. So the range of this data is 5. And for the second data, we can see that the largest value of the second data is still 6, while the smallest value is also 1. So the range of this data set is also 5. From these 2 examples, we can see that the distribution in example 2 seems to be less spread out than the distribution in example 1. But the range doesn't capture that. So the range is not a very accurate measurement to describe the dispersion. Therefore, we'll also need to use the following different measurements, like the variance. Here is a formula to calculate the variance. First, we use each value to minus the mean of all these values, and then we calculate the sum of the squares of these differences, and then divide it by the sample size, n. Okay, so here is the example. We have 4 data in the data set, and the mean is 10. Okay, so for each value we use is absolute value minus the mean. So the first one is minus 6. For the second one is minus 2. For the third value, the difference is 0. And for the fourth one, it's 3. For the last one is 5. Then we calculate the square of these differences. It's 36. Like the second one is 4. The third one is still 0. And the fourth one is 9. And for the fifth one is 25. Then we add all the squares together, equals to 74. And then we use this sum to divide the number of records, which equals to 5. So we use 74 divided by 5. Finally, we get the variance equals to 40.8. This formula shows the calculation of the standard deviation. We can see that first, we use the values to minus the mean, and then calculate absolute values of this difference, and then add them up and divide it by the number of the records in the dataset to get the standard deviation. And here is an example. The values are the same for us to calculate the variance. So we can see that the first step to calculate the standard deviation is also the same as the first step to calculate the variance. But then instead of calculating the squares, we calculate the absolute values of these differences, and we add them up. We got number equals to 16, and then we use this number to divide the number of records, which is 5, to get the standard deviation equals to 3.2. Okay, then the last measurement for the dispersion is coefficient of variation. Unlike the other dispersion measurements like the range, the variance, the absolute distribution, they are the absolute measurements for the data dispersion, while the coefficient of variance is the relevant measurements of data dispersion. It is calculated relatively to the mean. So this is formula to calculate the coefficient of variance. It's just to use the standard deviation divided by the mean. This example is for you to better understand the coefficient of variation. Suppose we have a data that has a mean of 200 and a standard deviation of 10, so that the coefficient of variation is just use standard deviation 10 divided by the 200, the mean. You can get the coefficient of variation equals to 0.05. So we can use the coefficient of variation to get this understanding that the standard deviation is 5% as large as the mean. So we can see that usually the larger the coefficient of variation, the more spread out the data is. Okay, then I'm going to show you how to use R to calculate this measurements of dispersion. Okay, so let's go back to R again. As the first measurement for dispersion is range, we're going to calculate range first. In R, there is not a specific function to calculate the range of a data set, but we can use its definition to do the calculation. Since range means the largest value minus the smallest value, so we can calculate the largest value using the function max. We here max of net pay, which is the largest value of the net pay column, and then we minus the minimum. We use the minimum function to calculate the smallest value of net pay. Okay, then we can get the range of net pay. We run this. Here shows the range of net pay is 2,494. Okay, then next we calculate the variance. In R, there is a function used specifically to calculate the variance of the data. It's called VAR. Then we just use this and type net pay. Just need to see the result. Here shows the variance of net pay equals to 314,988.9. Okay, then for the standard deviation, also there is a function SD in R. We use it on the net pay data and calculate the standard deviation of net pay equals to 561.2388. Then for the coefficient of variation, there is not specific function in R to calculate this, but then we still can use the S definition to do the calculation. As standard deviation of net pay divided by the mean of net pay. So we can see that the coefficient of variation is 0.309966. We can see from this value that the net pay data is not very spread out, but also not very centralized. Then that's for the dispersion. Another descriptive statistics for the quantitative data is the skewness. Skewness is a measurement of symmetry. The value of skewness can be positive or negative. A positive skewness indicates that the mean of the data value is greater than the median, and that data distribution is right skewed. And the negative Skewness indicates that the mean of the data values is less than the median, and the data distribution is left skewed. And this is the formula to calculate the skewness. Okay, in R, there is not a function that can be used to directly calculate the skewness of the data in the package that come with the R. But in the other packages, the function exists. So we should first download the package and then use the function. And now I'm going to show you how to download the packages in R. This is very important. Okay, first, you choose the packages here and choose Install Packages. And here there is a list of the mirror site that you could use to download the package. You just go down to choose the one in the USA. Choose this one. Actually, anyone in the USA should be fine. We just choose this one in California. Then we choose OK. And it will give you a list of the packages you could download. The packages we want to use that contains the skewness function is called moments. So we just go down to find the one start with M, the moments here. Here is a package. We just choose OK, and he will ask you to use a personal library instead. It's okay. Just choose yes, and then it will download the package automatically. Every time you want to use the function in the package, you have to refer this package first. And we have to use a function called library to refer the packages. So here, we first type the library. The name of the package is moments. And then we use the function in this library. This function is Skewness. We use this function on the NetPay data. And we run this script. Here shows the skewness value of this NetPay data is equals to 1.15711. So it's a positive value, which means that the distribution of the NetPay is skewed to the right. And the mean of the NetPays is larger than the median. Then let's go to the next, descriptive statistics, which is kurtosis. Kurtosis is a measure of the peakedness of the data distribution, and it can also be negative or positive. The negative kurtosis indicates that a flat data distribution, while positive kurtosis would indicate a peaked distribution, while the normal distribution has zero kurtosis. And this is the formula to calculate the kurtosis. Okay, then in the R, we also have the kurtosis function in the library moments. So before we use this function, we refer the package moments first, and then we use this function on the data NetPay. Okay. Okay, here in the right side, it shows the result of this calculation, and the value of kurtosis is 4.211895 for the net pay data. This number indicates that most of the values in the net pay data are concentrated in a small range of values. But there are not very small values and there are not very large values, which is true that most of the net pays are concentrated in the 1,500 to 2,000 area. Okay, so here are all the descriptive statistics for the qualitative data and the quantitative data. Well, for now, I just showed you the descriptive statistics for a certain attribute of a data set. But usually, if you got a data set, then you may want to know this descriptive statistics for each attribute. And there may be a lot of attributes in the data set. So if you do this calculation of descriptive statistics, one attribute by one attribute, it will be very time consuming. And there are also some functions in R to give you a general idea of all the descriptive statistics for all the attributes. Now I'm going to show you how to use these functions. In the package that comes with R, there is a function called SAPPLY, supply. You can use this function to get one descriptive statistics for every attribute. For example, I use this function on the employee master data to see the mean of each attribute in the employee master data. Then we first indicate the data is employee master, and the descriptive statistic I want to get is the mean. Okay, then let's see the result. Okay, here are the results. We can see that the mean can only be applied to the numeric data set. So we can see that the mean for the salary, the bonus, and commissions, and the pay per period. While for the other qualitative data attributes, it shows not applicable. Okay. While this function can only show you one kind of descriptive statistics to all the attributes, but there are also other functions can show you different types of descriptive statistics for all the attributes, but they are not in the package that come with R, so we have first download the packages. Okay. The first package we'd like to use is called Psych. Okay, we choose package, install package. The package starts with P, so we go down to the P. Psych. Okay, we choose OK. It will show the download has already finished. Then first we refer to this package, use library, psych, library psych. Then the function in this package we would like to use is called describe. So we just called describe. We still use the employee master data to do the demonstration. And then we run the scripts. can see here are the results. So we can see that for each of the variable in the employee master dataset, it shows the number of records, the mean, standard deviation, median, range, minimum value, maximum value, skew, kurtosis, etc. and etc. Okay, then the other package we can use is called pass test. It starts with P also. Here, pass text. Just click it to download and just refer it before use it. And the function in this library is called stat dot this user and employee master dataset. And see the result. And we can see that for each attributes in the dataset, it returns the number of validated values, the non-values, not applicable values, and the minimum value, maximum value, range, sum, the median, the mean, like the variance, standard deviation, coefficient of variance. So we can see that the descriptive statistics shows here is a little bit different from the descriptive statistics shows by using the describe function in the psych library. So the use of this summarized descriptive statistics functions depends on what kind of descriptive statistics results that you want to get. Okay, then another package I'm going to show you is called HMISC. So it starts from H. Here. We refer it first, HMISC. Then the function we want to use is also called describe. Then let's take a look at the result. Here it shows the result. We can see for each attribute in the data set, it gives the number of records, the missing value, unique value, the mean, and the 5, 10, 25, 50, 75, 90, and 95 percentiles. And the lowest 5 value and highest 5 value. So also the results of this function is different from the first two. Okay, so these are the three example of the summarized descriptive statistic functions in R. And usually these functions should be only used to the quantitative values, while for the qualitative values, like here, the first name, the last name, actually the result is not very meaningful. Then I'm going to show you another summarized descriptive statistic functions that could show the results of all the attributes in the dataset by groups. And it's also in the library of Psych. So I'm not going to download it again. We just need to refer it. Psych. And the function is called describe.by. So we first enter the data that we want to describe, employee master data, and the indicator of groups is like the work department. Okay, then let's see the result. Okay, you can see that it shows the descriptive statistics of all the values according to different work departments. This is group 1, the work department A00, and the descriptive statistics for each attribute is listed here. And then it lists the results for the group 2, work department B01, and also the group 3, work department C01, and etc. etc. So if you want to get descriptive statistics of the quantitative data by a qualitative data, this is the right function that you may want to use. Okay, then finally, let's take a look at the advantages and disadvantages of descriptive statistics. So the first advantage of descriptive statistics is that it is essential for arranging and displaying data, and it could form the basic of rigorous data analysis. The descriptive statistics will be much easier to work with, to interpret, and to discuss than the raw data. And it could also help the auditors to examine the tendencies, the spread, the normality, and the reliability of a data set. Actually, the descriptive statistics can be shown both graphically and numerically. In today's lecture, I just show you the numeric presentation of the descriptive statistics. And in our next lecture, which is the data visualization, I'm going to show you the graphical representation of these descriptive statistics. And the descriptive statistics also include useful techniques for summarizing the data, and it could form the base for more advanced statistic models. Well, there are also some disadvantages of descriptive statistics. If you don't examine like every type of the descriptive statistics, the result may be misused, misinterpreted, and incomplete. While if you get a relatively small data set, it may be not necessary to use these descriptive statistics. Well, some of these descriptive statistics demand a fair amount of calculation and explanation, like skewness, kurtosis, but using software it should be fine. So even though the descriptive statistics is very important for the auditors to explore the data, but it's not the complete analysis of the data. because it offers little information about the cause and effects, which may demand more advanced analysis. And it may be dangerous if it is not analyzed completely. Okay, so these are all the contents that we covered in today's lecture. Let me give you a brief review of today's lecture now. First, we discussed the types of data. There are qualitative data, which could be the nominal or ordinal. And there are quantitative data, which is usually the continuous data. And then we introduced the descriptive statistics for the qualitative data, include the absolute frequency, the relative frequency, and the category statistics. And then for the quantitative data, we introduced several types of descriptive statistics, including the frequency distribution of data. The measurements of frequency distribution of quantitative data include the absolute frequency, the relative frequency, the cumulative absolute frequency, and cumulative relative frequency. And then the second descriptive statistics for the quantitative data is the central tendency. And the measurements for the central tendency of quantitative data include the mean, the median, and the mode of the data. And the third descriptive statistics for the quantitative data is dispersion. The measurements of dispersion include the range, the variance, the standard deviation, and the coefficient of variance. And then we introduce the skewness and kurtosis. And finally, we introduced several functions in R that could display summarized descriptive statistics for the quantitative data.
I guess you have already experienced the power of R through Chi's lecture. I have also uploaded the data to eCollege. You can download them and replicate the analysis that you learned today. Remember that I have shown you how to download RStudio. Now I will demonstrate some advantages of RStudio compared with R, and I will also show you some additional useful comments in addition to what Chi has taught. The first thing I want to demonstrate is to import data. In R, you have to write code to import the dataset. In RStudio, this step is simplified for many data types. Here, I will also use employee master data as an example. So once you open RStudio, this is the interface that you will see. First, you need to new script, and this is where you need to write your comment. On the upper right, you can find this import data option. Because employee master data is in text format, so we choose from text file. And then we choose this file that we want to import. Then you can see there are several options to adjust your input. First, you can rename your dataset, but we keep it as the original one. Then you can choose whether the first row is the heading of different variables or not. If you choose not, you can say it will assign a new variable name for this, but we will choose yes because they are variable names. And the separator is to determine how your file is separated. If you can open the original file, you would notice that different components are separated by tab. Decimal is to see how the numbers are divided. Let's go to the end of the file, and you can see these numbers are separated by period, not comma. So we choose period. Quote is to see how these characters are separated from others. For instance, in this case, we can see these characters are actually coded by double quote, not single quote. So we choose double quote. And any string is to choose which character you consider as a null value, and here we set it as default. Now let's import the dataset. You will find that the dataset is automatically opened. You can easily view it. This is very convenient. In addition, on the upper right, the imported data is showing here. If you import more datasets, they will also be displayed there. It's very easy to manage. Simply click it and it will lead you to the dataset. There is no need to type in again the name of the dataset to see the data. You can also use one button to clear all the dataset, like this one. For now, we don't delete it. Now, you have already seen how to load the package in R. Before you can use functions in packages, you need to first install the package and then use library function to load it to your program. In RStudio, searching for packages is easy, as can be seen here. You can search by first letter. For example, if you want to load the psych package, you can type P, S, Y, and you can see this package. You can choose it. This is more convenient than R. It should be noted that the packages downloaded in R and RStudio are separate. They are not the same. If you installed some packages in R but not in RStudio, you cannot use them in RStudio, and vice versa. Sometimes the console could be very messy after you typed in a lot of commands. A useful tip to clean up console is to enter Ctrl and L at the same time, like I did here, and now it's fresh. This also works for R. Another useful tip is to fix a dataset. For example, in this case, you need to specify the name of the dataset first and then use a $sign followed by the name of the variable. Let's see, salary. You have to specify it in such a way to find the values in salary. If you simply type in salary, it will return object salary not found. Sometimes you may be only working on one dataset or a limited number of datasets, and this is very inconvenient. So one command that you can use is attach. First, you can attach the dataset, and after this, you can simply use the name of the variable to find the values in it, and there is no need to type in employee master, $sign, and salary. If you want to stop this function, you can use the detach function. And now, if you only specify the name of the variable, it will return the same thing. Sometimes the dataset contains many observations, and you only want to see the value of the first several observations or the last several observations. In this case, you can use head and tail function. Now let's see how it works. But before this, I will attach this for convenience. And then we can use head function for salary. You can see the first 6 observations under this value. And if you use the tail function, you can see the last 6 values in this data set. If you have too many data sets loaded in R or RStudio, you can choose to list the name of all data sets. Simply use the function ls. And you can see here that for now there is only one data set imported. And if you want to remove some of these data sets, you can use rm function, and you put the name of the data set in the bracket. As you can see here, the environment is empty and no data set is imported for now. Finally, let me show you how to select observations based on your specific requirement. This requires you to use subset function, which is one of the most widely used commands. Let me first import the dataset again. And now, for example, you want to find all those observations with commission larger than 2000. Then we create a new dataset called large commission. Subset. First specify the original dataset, comma, and then the condition that you want to specify. In this case, it should be commission larger than 2000. And you can see here, there are only 25 observations left. You can also specify 2 or more conditions. For example, you may only want to keep those observations with females and also commissions that are larger than 2000. So here we create another dataset, large commission F, subset, employee master, commission larger than 2000, and 6 F. Notice that you have to use double equal sign here to specify equals to. You cannot use one equal sign. And now let's run it. As you can see now, we have only 13 observations with females who has commissions larger than 2000. And finally, you don't need to keep all the variables. In the subset function, you can choose to keep variables that you are interested in. For example, you may want to keep only first and last names, work department, commission, gender, and salary. So let's create another dataset. Still the subset function. Employee master data, commission larger than 2000, and sex equals female. Now you need to use select function. Select equals C bracket, first name, last name, work department. This is case sensitive, so you should be very careful. Salary, Okay, these are the variables that we want to keep. And now run this command. And you can see the newly generated dataset contains only 6 variables. Now let's have a look at the new dataset. You can see it's very clear, and you can conduct further analysis on this dataset. To conclude, I believe you have already realized how powerful R can be. You can explore all different kinds of functions and play with them. We will continue to use R for visualization purposes in next lecture. See you next time.